Welcome back. So what I would like to talk about today is a technique called the method of Lagrange multipliers. And by the end of the day, we should be able to use this technique to find the absolute maximum and the absolute minimum of a function of, I've listed a function of three variables here, f of x, y, and z. And you can also use it to find the maximum and minimum values of a function of two variables, f of x, y. But there's an extra little bit of interest here. We don't want to just find the absolute minimum and maximum of this function, but somewhere along the line, someone has come in and put an extra restriction on the values of x, y, and z, which we're allowed to input into the function, which is represented by a constraint equation, g of x, y, z equals k. To give a concrete example, let's go to the two variable case. Let's consider this problem where they're asking us to find the maximum and minimum values, if they exist, of the function f of xy equals x squared plus y squared. So we want to minimize and maximize the output of that function. Now, this function, as you recall, has a graph in the shape of what's called a paraboloid, which looks like a parabola that's just been spun around so that it has a bowl shape. And if we're allowed to take any point on this entire parabola, the absolute minimum of that paraboloid will be 0, located at the origin, because that's the lowest point on this entire graph. But someone has come in and added a restriction on the points that I'm allowed to consider when I'm finding the minimum and maximum values. They say whatever x and y you consider, it should satisfy the equation x times y equals 1. So that means the point 0, 0, which is normally the absolute minimum of f of xy, this point no longer counts because it doesn't satisfy the constraint equation. So the question is, among all the points x, y which do satisfy the constraint, which one will give us the highest value from f of xy, and which one will give us the lowest value? Now, as a way of visualizing this problem, let's go out to Desmos for a minute, and here I have set up a contour map for the function f of xy. Here, toward the center, is the level curve corresponding to z equals 1, moving out corresponding to z equals 2, then level 3, level 4, and level 5. So, as expected from the graph of the paraboloid, these elevations are getting larger as we move away from the origin. Now suppose that I come in and I type in the constraint where I require that x, y must equal 1. Okay, and let me put that, let's change the color of that just for a minute to make it really stand out. I am restricting myself to plugging in points x, y, which lie along this white curve here, the curve x times y equals 1. The question is, among all the points on the white curve, x, y equals 1, which point or points will give me the lowest output value and which ones will give me the highest output value? So let's go ahead and let's develop a technique that can be used to answer this question, as well as even more complicated versions of this problem. Method of Lagrange multipliers, which is designed precisely for a scenario like this one, where you're trying to maximize or minimize the value of a function of 2 or 3 variables, subject to some constraint that must be satisfied, and we'll call the constraint equation some relationship between g and y, g of xy, must equal k. And we do assume that whatever this function g is, its gradient is non-zero. Step number 1, and this is usually a pretty lengthy step, we introduce a new variable which is called lambda. That is the Greek letter lambda. And then we try and solve a system of two equations. The first equation that we solve is we try to make the gradient of the function f that we're trying to maximize equal to lambda times the gradient of g, the constraint function. And simultaneously, we try and solve the constraint equation. We want to find points x, y, which make both of these two equations true at the same time. And finally, we plug the points from step 1 into f of x, y to see which points will give us the largest outputs and which points give us the smallest outputs. The largest outputs will correspond to the maximum value of the function. The smallest output will correspond to the minimum of the function. Let's say largest output, which give the smallest output. Now, I think in terms of just abstract steps, this may not make any sense in the moment, so let's put this into practice right away and apply it to that motivating exercise that we talked about at the beginning of today's video. Let's find the maximum and minimum of the function f of x, y equals x squared plus y squared, subject to the constraint x times y equals 1. Okay. Now here is our constraint equation. G of xy equals a number. So our g of xy is equal to x times y. And we need to solve two equations. Gradient f equals lambda times gradient g, and solve constraint equation equals k. Now in our particular problem, let's find the gradient of f and the gradient of g. The gradient of f, the gradient of x squared plus y squared, is the vector in the first coordinate, the partial derivative in the x direction, and then the partial derivative in the y direction of x squared plus y squared. And then, for g of x equals x times y, its gradient, we find the partial derivative in the x direction by power rule, that's just equal to y. And likewise, the partial derivative in the y direction is the other number x. So we need to now solve this, and we need to make sure that xy equals 1 is satisfied. Now, although this system looks like it only contains two equations, it really contains three. Because for the first equation, if we want to make these two vectors match up, they have to be exactly the same, not just in their x coordinates, but also in their y coordinates. So if I look at the x coordinates, that says that 2x must be equal to lambda times y. And if I look at the y coordinates, that says that 2y must be equal to lambda times x. Then finally, with the constraint equation, xy equals 1, I have 1, 2, 3 equations that I have to solve containing 1, 2, 3 variables. And if you've taken any linear algebra before, you'll remember perhaps that when we are solving systems of equations, if you want to be able to reliably get a solution, the number of variables in your equation needs to match the number of equations that you have, which is why we introduced this third variable called lambda. We introduced a third variable so that the number of variables and the number of equations would match, so that we would have 3 of each. Now, to solve these systems, the typical process involves a bunch of substitution. For example, my attention goes first to this equation here on the right side. Because unlike the other two equations, this one is a little bit simpler and it only contains 2 variables instead of 3. So that means that I can, for example, isolate y equals 1 over x, and I can use that and substitute that into the other two equations, and I will get 2x equals lambda times 1 over x from the first equation, and I will get 2 times 1 over x equals lambda over x from the second equation. Well, now I can play the same kind of game with this second equation, rather the first one. I can isolate lambda by multiplying both sides by x to get the statement that lambda must be equal to 2 times x squared. And then I can substitute that information into equation number 2 to say that 2 over x must be equal to 2x squared times x. And after multiplying both sides by x and dividing both sides by 2, this tells me that 1 must be equal to x to the 4th power. And there are only 2 real numbers which do that job, x equals 1 and x equals minus 1. Well, having found that, let's go ahead and find the corresponding y values with the relationship y equals 1 over x. If x is positive 1, then the y must be positive 1 as well. And if x is equal to negative 1, the reciprocal will also be negative 1. Okay, so what we have found so far are 2 values of x and y that are candidates to be the absolute maximum and absolute minimum of the original function subject to the given constraint. Now let's try and figure out which of these, if either, is the absolute max and which is the absolute min. So let's start by plugging these points into the function. Let's start with the point x equals 1, y equals 1. 1 squared plus 1 squared is 2. Then let's check the output that we get from negative 1, which is negative 1 squared plus minus 1, which is 1 plus 1, which is 2. Okay, now we got exactly the same output from both of these, which means that the value 2 is either the absolute max or the absolute min. Now, unfortunately, as of this moment, we don't have any other outputs of the function with which to compare this given value of 2. We got the same output from both of our points of interest, and so we don't have any other outputs that we can compare to say whether this point is larger than the others or smaller than the others. At this point, though, we can go back to Desmos, have a look at our level curves, and see if the level curves give us any hint about whether the points that we found represent absolute minima or absolute maxima for our function. Now, the points that we have found are the ones that are located right here and right here, where the graph of the function xy equals 1, the constraint equation, where that just touches the level curve drawn in orange, the level curve corresponding to level 2, which is why we got an output of 2 from both points. So because of that, let's look at every other point on this constraint equation. Every other point on this constraint equation is going to be further away from the origin than these corner points that we found, -1, -1. And because those points are further away from the origin, they're going to lie on level curves which have higher elevation values. For example, this point lies on the level curve z equals 3, which has a higher value than z equals 2, the level curve here. So from the level curves, from observing the level curves, this value of 2 corresponds to a absolute minimum, the lowest possible value of this function amongst all the points on the constraint curve. The absolute minimum is 2. Now the only value that we found from method of Lagrange multipliers was 2, and it was the absolute minimum. Because of that, there is no absolute maximum. There is no absolute maximum of this function subject to this constraint. And we can see that as well from these level curves. As we move along the constraint curve further and further away from the origin, the value of our function is just going to keep growing without bound. So there is no highest topmost value that we're going to get from the function f of xy. The function will just keep growing and growing as we move further and further out on this constraint curve. So that is an example of finding the absolute minimum subject to this constraint in the case that there was no absolute maximum. Let's try another example, this time with 3 variables instead of 2, but to compensate for that, we've made the actual function a little bit simpler. F of x, y, z is equal to 2x plus 6y plus 10z, subject to the constraint that x squared plus y squared plus z squared must be equal to 35. Now, this function here, the constraint function, set equal to 35, as before, represents our function g. So our journey begins by finding the gradient of f and the gradient of g. Now, the gradient of a function in 3 dimensions means exactly what you might expect at first glance. In the x position, the derivative with respect to x. In the y position, the derivative with respect to y. And in the z position, the derivative with respect to z. So for our problem, if we take the derivative with respect to x, treating both y and z as constants, all that we'll get is the slope in the x direction, 2. The slope in the y direction then is 6, and the z direction is 10. Similarly, the gradient of g has the g sub x quantity, partial derivative, in the first component, 2x, and then the derivative with respect to y, 2y, and then with respect to z, 2z. So our goal is now to solve the system 2, 6, 10, the gradient of f, is equal to lambda 2x, 2y, 2z, and we also require that the constraint function must be satisfied. So let's go ahead and analyze this. If we take the first component of the gradient equation, this tells us that 2 is equal to 2 times lambda times x. If we take the y component of the gradient equation, lambda 2y, this tells us that 6 is equal to lambda times 2y. If I take the z coordinate, that tells us that we must have 10 equal to 2 times lambda times z. And finally, we also require that the constraint equation must be satisfied. Now, of all the equations in this problem, this time I think the constraint equation is the most complicated. So I think it might be easier to try and work and manipulate the 3 gradient functions equations first, and to see what we can get in terms of information out of that. For example, the equation on the left-hand side tells us, after we simplify by canceling the 2 on both sides, that x must be equal to 1 over lambda. The equation here in blue, after we divide both sides by 2, tells us that 3 over lambda must be equal to y. And the equation here in pink, if we divide by 2, tells us that 5 over lambda must be equal to z. Well, now let's see what happens if we substitute all 3 of these equations into our constraint function. Everywhere there was an x, we can replace that with a 1 over lambda. So we have 1 over lambda squared. Instead of y squared, we can now write 9 over lambda squared, since y is equal to 3 over lambda. And instead of z, we can now write 25 over lambda squared, and that should be 35. Now if I add this equation up, if I simplify it, we get on the left-hand side 35 over lambda squared is equal to 35. Or, in other words, lambda squared is equal to 1. Which leads us to 2 possibilities. Lambda is equal to 1, or lambda is equal to minus 1. Now, we're not actually looking for lambda, so it might at first glance seem like this was a waste of time. But we can plug these values of lambda back into these 3 equations to get the values of x, y, and z, which we're really looking for. So for example, when lambda is equal to positive 1, if I plug that quantity into all 3 of these fractions, that tells me that x must be positive 1 as well, y must be positive 3, and z must be positive 5. If lambda is equal to negative 1, all these points change to their opposites. X is equal to minus 1, y is equal to minus 3, and z to minus 5. Now let's plug these into the function, and let's see if we can deduce which one will give us the absolute maximum and which one will give us the absolute minimum. Oh boy, we're running out of space. Have to be careful. F of 1, 3, 5. Let's go back and remember what the function actually was. This function was 2x, 6y, 10z. So let's go ahead. 2, 1, 6, 3, 10, 5. So this is going to be a fairly large positive number. This is going to be 50 plus 18, so that's 68 so far. This is going to be 70. If I go in and plug in negative 1, negative 3, negative 5, the entire expression changes to its opposite. And so I'll get negative 70 from that. So unlike in the previous example, we have a pretty clear indication of who is the max and who is the min. And that is method of Lagrange multipliers in the case of 3 variables instead of 2. An even lengthier process because this time we have a system of 1, 2, 3, 4 equations containing 4 variables, all of which need to be solved for in order to get the points which are candidates for our max and min values.